Hello and welcome to today's class. Today we're going to be continuing to look at slope and deflection of beam theory. This is the second of two videos. In the first video we used the direct integration method, which you can use for simple cases. We looked at some simple cases, cantilever beams with point loads on them and UDLs on them. Simply supported beams with point loads and UDLs on them. You can use those simple cases, and you can also use the principle of superposition for those simple cases to understand the slope and deflection of beams of certain structures. However, if the moment is not constant along the length of the beam, i.e. you've got a more complicated structure, there's multiple loading points or multiple boundary conditions, multiple supports and so on, then you're unable to use those simple techniques that we discussed last time. You will need to use something called Macaulay's method, and that is what we're going to be looking at today. So today we're going to carry on looking at slope and deflections of beam theory, and we're going to be looking at Macaulay's method to deal with those more complicated load cases. So if you haven't watched that first video already on the direct integration method, please do that before watching this video, and then once you've watched that, then we can then talk about the more complicated cases shown in Macaulay's method. If we have a look at the handout which I uploaded last time, so this handout here, slope and deflection of beam theory, we talked about the basic concept. The flexural stiffness times by the second derivative of the vertical displacement is equal to our moment. We're going to use that, but we're going to consider what happens now if that moment changes. Okay, so last time we looked at these simple cases, the cantilever beam with the point load on it, the cantilever beam with the UDL on it, the simply supported beam with the UDL on it, and the simply supported beam with the point load on it. I actually only went through the first example, the cantilever beam with the point load on the end. I think it's the first one. Yeah, and then asked you to look at the subsequent examples. So hopefully you've had a chance to do that. There is the cantilever beam with the non-uniformly distributed load. So that's in there for completeness. I don't expect you to look through that. I don't expect you to have done that. There's some examples there. Please have a look at those if you've not done already. And then this is what we're going to start looking at today. Okay, Macaulay's method. So it deals with more complicated scenarios when the moment changes along the length of the beam. So we'll have a look at that, how to use it, why it works, and then we'll have a look at some worked examples doing that, using that. Okay, so let's consider a scenario where we've got some sort of structure. We've got some sort of moment on that structure. So here's our beam. I don't know how it's supported. We've got some sort of moment from some sort of loading being introduced in the beam here. And then we're going from left to right along the beam. We get to position A and another load Q is introduced. And then we travel a further distance, small a, along the beam until we get to position B, and then yet another load is introduced, W. Okay, so clearly as we go along the length of the beam, the moment is changing due to the fact that we're introducing additional loads. Okay, so this is what we said last time. Our moment was equal to EI d squared y by dx squared. Okay, now between A and B, clearly the moment is not just m. Between A and B, so we've gone past Q now. We've got an additional moment. So we're between A and B. And if we were to look left, we've got our moment already M. And we've got an additional load Q, which is, if we consider X, the origin X to be here, we've got X meters along the beam. So we're X meters away from Q. So the moment caused by Q is QX. Okay, so if we take our slope and deflection of beam theory from last time, not only have we got our moment, we've also got this moment caused by QX, this additional load which has been introduced. So this is just between A and B. So we've got EI d squared y by dx squared equals our moment plus QX. If we apply what we learned last time, let's integrate that once and we'll get the slope. Okay, so EI dy by dx equals mx. plus qx squared over 2 plus c1. This time I'm calling my constant c1. We can have various constants, so I'll call them c1, c2, c3, c4, and so on. Last time we just referred to them as a and b, but this time I'm calling my constant c1. So we've got a constant of integration there, c1. Okay, and then based on what we did last time, what we learned last time, let's integrate that again. So we're using the direct integration method here. And we'll end up with EIY equals mx squared over 2 plus qx cubed over 3 plus c1x. So we've integrated our constant of integration with respect to x plus c2. So there's nothing different there really compared to what we were doing last time. We've just introduced a new moment at the start here called qx, which is related to the fact that we've introduced this new load. So that's between A and B. We've got equations 1, 2, and 3 there. Okay, now beyond B, we've introduced yet another load, okay, W. So things change again. So we've got EI d squared y by dx squared equals m plus qx. So q is still there. Remember, we've gone past q. We're x meters along the beam. We're here now. We've gone x meters along the beam, so we've got this moment here, but we've got yet another term there which has been introduced by the fact that we've got this load W on the beam, and that is minus because it's downwards. That's kind of arbitrary. We'll consider it downwards. It doesn't actually matter. So we've got minus W, and if this distance from here to here is x, and this distance from here to here is a, this distance from here to here would be x minus a. Okay, so that's where that comes from, x minus a. Okay, so that's what's happening beyond B. We've got equation number 4 there. If we were to integrate that with respect to x, which is what we were doing last time, we're going to have EI dy by dx, our slope, equals mx plus qx squared over 2. And then let's take these terms here. We're going to take those brackets, we're going to expand them, and then we're going to integrate each term with respect to x. So this first term would be minus wx. We integrate that with respect to x, so that becomes minus wx squared over 2. This next term would be minus w times by minus a, so that's plus wa, so that becomes wax. And then we've got yet another constant of integration here. We'll call that C3, our third constant of integration. We don't know what that is. We'll come on to that. Again, we'll integrate that with respect to x to get from our slope to our deflection. So we're going to end up with EIY equals mx squared over 2 plus qx cubed over 6 minus wx cubed over 3 plus wax squared over 2 plus C3x plus C4. We've introduced yet another constant of integration there, C4. Okay, so we've got quite a complicated scenario now. We've got 6 equations. Okay, there's the second derivative of the vertical displacement between A and B, and there's the second derivative of the vertical displacement beyond B. Okay, you can see we've just introduced another term there, the term which was introduced at position B there, minus W. And that leads to that term there. We've then got the slope between A and B, and we've got the slope beyond B. Okay, and we got that by expanding this bracket and integrating all of those individual terms with respect to x and adding our constant of integration on there. And then we've got the deflection between A and B, and we've got the deflection beyond B. Okay, again, think how we arrived at that. We expanded this term here, this term which was due to that load. We expanded all of the individual terms. We integrated all of those with respect to x, and then we've added our constant of integration. So we've now got 4 constants of integration, C1, C2, C3, and C4. So that's what's happening. Now, we've got between A and B here, and we've got beyond B here. Okay. But what we do know is at B, they should be the same, the slope at B is the slope at B, and the slope, the deflection at B is the deflection at B. So between A and B, so at position B, when X is equal to A, this is true, but also this is true. We also know that the deflection when X equals A, the deflection at B should be given by this, should also be given by this. Okay, so let's now consider the implications of that. Let's look at these equations. We've got these 6 equations here. So it says here, look, the slope at B is the same. Therefore, using equations 2 and 5. So equation 2 shows me my slope between A and B. Equation 5 shows me my slope beyond B. But at B, actually, the slope should be the same with this equation, and it should be the same with this equation. So let's take equation 2 and equate it to equation 5. Now, that's only valid at B. Okay, and that's what we've done there. We've got equation 2, we've got equation 5. Now, at B, X is equal to A, so we can, there we've got MX, look, we can replace that with MA. There we've got QX squared over 2, we'll replace that with QA squared over 2. So X is equal to A, so we'll plug A into our equation there. And then we've noticed we've got MA on this side, we've got MA on this side. We've got QA squared over 2 on this side. We've got QA squared over 2 on this side. So we can massively simplify that equation, and we end up with an equation for C3 in terms of C1. So we know our third constant of integration in terms of our first constant of integration. So what we can do now is we can actually take that, and rather than have, so we're going to put that into equation 5 here, look. Rather than having the slope with this third constant of integration, let's replace that third constant of integration and put it in terms of the first constant of integration, C1. So we'll plug that in there. So there's that equation, look. And now instead of writing C3, I'm going to write this term here. So this term here, you can see that is what we've just calculated. That is C3. Okay, so we've put C3 into that equation. So now we've got that equation, but instead of having our third constant of integration, we've got our first constant of integration in there. Okay, and then we just factorize that, and we end up with this equation here, equation number 7. And what we've got there now, and remember how we arrived at that, we've got our slope of our beam beyond B, but instead of having our third constant of integration in there, we've now got our first constant of integration in there. In the same way, so we've just said our slope at position B should be given by equation 2 and 5. We also know that the deflection at position B should be given by equations 3 and equation 6. So let's now equate those and say that X equals A. So that's what we're doing here. So we've equated those. We've said that X is equal to A. We've simplified those. We have put in, so we've now got C1 and C2, C3 and C4. We can replace C3 with this equation here, look. So we'll plug that in. C1, C2, there's C3, look. So we've plugged that into there, look. So we've put C3 in there, so we've got rid of C3. We've got it in terms of C1. Again, we'll simplify that as much as we can, and we end up with this equation here. We've now got C4 in terms of C2. So in the same way that we did before, we plugged, we wrote, where is it, this equation here, but instead of writing C3, we wrote it in terms of C1. Now we can do the same thing here. We can rewrite this equation, and instead of using C3, we'll use C1 like we did before, and instead of using C4, we will use C2, because we've now got that here, look. So there's C3, place C3, with it in terms of C1. We've replaced C4 with it in terms of C2. And then we do a bit of algebra manipulation. We expand those, we factorize those, and we end up with our deflection beyond B in terms of C1 and C2. Now, let's summarize that. So what's happening beyond B? So up until B, we've got, there's my second derivative of the vertical displacement. There's my slope in terms with C1 in it. There's my deflection with C2 in it. Beyond B, when we introduce yet another load, we've now got the moment equation that we came up with here. And then for the slope, instead of thinking of equation 5, because that's got C3 in it, let's take my slope here with C1 in it. And then for the vertical displacement, instead of equation 6, which has got C3 and C4 in it, let's take this equation here that we've just calculated, which has got C1 and C2 in it. Okay, equation number 8. So there's those three equations written out there. Okay, so beyond B, that was my original equation, the moment. And there is the slope with C1 in it. And there is the deflection with C2 in it. Now, notice what's happening there. We've got M plus QX minus WX minus A. Okay, for the slope, we've got M has become MX, QX has become QX squared over 2. And in this term here, this is actually called our Macaulay's term. So whenever you see a Macaulay's term with a number minus x minus a number, that tells me that where that load is being introduced. We've got that load W being introduced A meters along the beam. Okay, but notice what's happened to that Macaulay's term. We've taken that Macaulay's term, and instead of expanding all of those terms and integrating them with respect to x and getting yet more constants of integration, which is actually what would happen, we can just take that Macaulay's term, and instead of integrating it with respect to x, which is what we've done with all of these other terms, let's integrate it with respect to this bracket. So minus wx minus a becomes minus wx minus a squared over 2. Okay, now mathematically that's not correct. That's not actually what happens. But we've used Macaulay's method there, and we've said, okay, instead of expanding that bracket and integrating all of those terms and adding more constants of integration and then simplifying those and doing lots of algebra and manipulation, which is actually what would happen, we can just take that Macaulay's term and we can integrate it with respect to itself here. Look, that there. We can say straight away would become that. Okay, so minus wx minus a becomes minus wx minus a squared over 2. And then we've got a constant of integration on the end there. To get to our next term, we can do for the vertical deflection, we can integrate it again with respect to x. So mx becomes mx squared over 2. Qx squared over 2 becomes qx cubed over 6. And then this term, the Macaulay's term, look what's happened to it. We've integrated it again with respect to the Macaulay's term. So minus wx minus a squared over 2 becomes minus wx minus a cubed over 6. C1 becomes C1x, and then we've got another constant of integration. So that's what happens with Macaulay's method, is we can understand what's happening beyond B once we introduce an additional load, simply by taking the Macaulay's term and integrating them with respect to themselves. Okay, so there we've got x minus a as a Macaulay's term. So that's how we would go about using Macaulay's term. So let's now have a look at a few examples using Macaulay's terms. Now there's a couple of things, Macaulay's method, there's a couple of things which we need to consider. If we look at the original equations that we came up with, equations 1 through to 6 here, look. So between A and B, we've got m plus qx. Beyond B, we've got m plus qx. And then we've got this additional term, minus Wx minus a. Now that term is there because beyond b we have gone past w. So now if we consider x minus a, if x minus a is 0, we're at b. If x minus a is positive, we've gone beyond b. Okay, so if x minus a is positive, we must consider the moment which has been introduced by that load w, because we've gone past that load. However, if x minus a is negative, we are here, we're between a and b. We haven't gone past w yet, so we don't need to consider that term. So if we consider those 6 equations, we've got this term here, we've got this term here. Actually, if we consider that term there, if that is 0 or negative, if we just, that means we haven't got to that load w yet, so we can just ignore that term and we go back to this equation, look, m plus qx. Okay, so we must remember that when we're dealing with Macaulay's, when we're using Macaulay's method, if we look at the Macaulay's term, if they're 0 or negative, we just ignore them because that means we haven't got to that point W yet. So let's consider a few rules when using Macaulay's method. Okay, and then we'll have a look at a couple of examples using Macaulay's method. So let's take the origin at the left-hand end of the beam. Usually that's what we do. We start at the left-hand end and we work our way right. We go past all of the moments, all of the loads, and we write down the moments at the extreme right-hand end of the beam before we get to the other support. But at the extreme right-hand end of the beam, or at the right-hand end of the beam, once we've gone past all of our loads, so the most complicated scenario, we're going to write down the moment for that. We're then not going to simplify the moment equation by expanding the terms and involving the distance and then integrating with respect to x and all that sort of stuff, which is what we did when we proved why it works. Instead, we're going to integrate, keeping all of the bracketed terms within brackets and integrating the brackets as if they were single variables. We're then going to apply the resulting equations to any parts of the beam, but neglect all terms within the brackets when they are negative or if they are 0, okay, for the reasons that we've just discussed. Okay, and then point 6 here discusses a couple of special cases, what happens when we deal with UDLs if they don't go to the end of the beam, for example. We'll have a look at a couple of examples where we discuss how we'd go about using that. But to start with, let's look at the first 5 points and use Macaulay's method. So we'll start at the left-hand end of the beam, we'll go to the right, we'll pass all of the loads, we'll write down the most complicated moment equation, we'll then integrate it using Macaulay's method and then apply it just like we did with the direct integration method by looking at the boundary conditions and working out the constants of integration and therefore working out the slope and the deflection on the beam. While we're doing that, if there are any 0 or negative Macaulay's terms, we're just going to ignore them. Okay, so let's have a go at that. Let's have a go at using Macaulay's method. Okay, so let's have a look at an example with simple point load. So look at this example here, Macaulay's method. Okay, so an example with point loads. There we've got an example of a beam, and we can see that there are multiple loading points along that beam. So our simple scenarios that we dealt with last week or last time wouldn't be able to find a solution for that beam. So we're going to have to use Macaulay's method. So let's have a look at that solution. So our example with point loads. There we've got our example, and with point loads, we've got a reaction of 15 kilonewtons at this end of the beam. We go 3 meters along the beam, then we've got 20 kilonewton load acting vertically downwards. Then we go another 3 meters along the beam, we've got 10 kilonewtons acting vertically upwards. We then go another 4 meters along the beam, we've got 30 kilonewtons acting downwards. And then if we go another 2 meters along the beam, we've got our other reaction, RB, at this end of the beam. Okay, so what we're going to do, we're going to start at the left-hand end of the beam. We're going to go along the beam until we've passed all of our loading points. So we're going to pass the 20 kilonewton load, past the 10 kilonewton load, past the 30 kilonewton load, and we're going to write down the moment equation at position XX, where our bending moment equation is going to be the most complicated. So we're at this position XX. So we're at this position here. We're going to look left and we're going to write down any moments on the, acting on the beam from this position here. So, okay, so position XX. So we've got origin X equals 0 is at the left-hand end of the beam. Remember, we've gone X meters along the beam. So we're here at position XX. So the first thing that we need to consider is the reaction, RA. RA, that's 15 kilonewtons, okay, and that is X meters away from where we are. So the moment caused by that is going to be 15 kilonewtons times by X. Now, in a minute, we're working in kilonewtons, so we'll divide through by 1,000, but for now, let's just say 15 times by X. So there's that term there, 15 times by X. So that's the moment caused by that reaction load. Next, we've got our 20 kilonewton load. Now, our 20 kilonewton load is acting downwards. Okay, so that's why we've got minus 20. Okay, now how far away is that? Well, if this distance here is X, from here to here is X, and this distance here is 3. The distance from here to X, this distance here, is going to be X meters minus 3. Okay, so X minus 3. So that's where that term comes from. Okay, and notice what we've got there. That's a Macaulay's term, an X minus 3 there. Okay, so minus 20 because it's associated with this minus 20 kilonewton load, and then X minus 3, that's the distance that it is away from us. Next, we will consider the 10 kilonewton load. There's our 10 kilonewton load. And in fact, let's use another color. We've already used blue. Let's use green, for example. Okay, so our 10 kilonewton load. There's our 10 kilonewton load. Okay, so acting upwards, so it's positive 10. And that is, this distance here is X, and this distance here is 3 and another 3. So that's going to be X minus 6. X minus 6. Okay, that's where that term comes from. Okay, so remember what we're doing here, we're writing down our bending moment equation at position XX. Next, we will consider, let's take another color, I don't know, this gold color here, our 30 kilonewton load. Now 30 kilonewton load is acting downwards, so therefore it's negative, so minus 30, and its distance from here is going to be X minus 3 minus 3 minus 4. So X minus 3, 6, 10, X minus 10. Okay, there's that term there, X minus 10. Okay, so that's how we get to the bending moment equation. And like I said earlier, that is the bending moment equation at position XX, where we've gone past all of our loads. It's about, or it is as complicated as it gets. Okay, what we're going to do now is we're going to do what we did before. We're going to integrate all of this once to get the slope. We're going to integrate it again to get the deflection. Okay, when we do that, we're going to use Macaulay's method. So if any of these terms are 0 or negative, we're just going to ignore them. Okay, we've got EI d squared y by dx squared is equal to this lot. Okay, now remember I said earlier, we've written all our forces in kilonewtons, so therefore we need to divide through by 1,000 on this side, because we've divided through by 1,000 on this side because all my forces are in kilonewtons. Okay, so we need to keep our equal sign. We need to do the same on both sides. Okay, so we've divided through by 1,000 here, so therefore we must divide through by 1,000 here. Okay, so 15x becomes 15x squared over 2. Okay, so you can see there is that term there. Okay, minus 20 x minus 3. Now remember, instead of expanding all of those terms and integrating those with respect to x and then factorizing them, we're just going to use Macaulay's method, and we're going to integrate this term with respect to itself. So minus 20x minus 3 becomes minus 20x minus 3 squared over 2. Minus 20x minus 3 squared over 2. Okay. This next term, this green term, we've got 10. Again, it's the Macaulay's term, 10x minus 6. So instead of expanding all of those terms and integrating them all individually with respect to x and then factorizing them, we're just going to say 10x minus 6 becomes 10x minus 6 squared over 2. 10x minus 6 squared over 2. That's that term there. And then finally, the last term, this one here, 30 x minus 10. Again, it's a Macaulay's term, so it becomes minus 30 x minus 10 squared over 2. There's that term there. And then we've got our constant of integration, a. So let's circle that in pink. There we've got a. Okay, so that is the slope anywhere on the beam. And then the deflection anywhere on the beam again. So 15x squared over 2 becomes 15x cubed over 6. That is that term there, look. The red term, minus 20x minus 3 squared over 2 becomes minus 20x minus 3 cubed over 6. And then we've got the green term, 10x minus 6 squared over 2 becomes 10x minus 6 cubed over 6. And then the gold term, minus 30x minus 10 squared over 2 becomes minus 30x minus 10 cubed over 6. And then we've got our constant of integration. A becomes ax. And then we've got another constant of integration, b. The end here, this light yellow colour, b. So we've now got 3 equations. This one here tells me my bending moment. So it's this EI d squared y by dx squared is equal to that. Then we've got an equation for the slope, an equation for the deflection. So let's now look at our boundary conditions so that we can try and work out what those constants of integration are, what A and B are, in the same way that we were doing last time. Okay, so we're going to look at this beam. Now, where do we know the slope and where do we know the deflection? Well, we don't know the slope anywhere, actually, because of the complicated way it's loaded. But we do know the deflection in 2 places. We know that the deflection here, when x equals 0, is 0, assuming my rigid supports are infinitely stiff. So when x equals 0, y equals 0. We also know at this end, when x equals 3, 6, 10, 12. When x equals 12, y equals 0. Again, assuming that my support is infinitely stiff. So we can take those 2 boundary conditions and work out my 2 constants of integration. So let's look at, we're looking at this equation here. We're working out y. Okay, so first boundary condition, when x equals 0, y equals 0. So if x is 0, that term is going to be 0. If x is 0, now this is where if x is 0, we're just going to ignore that term because we haven't got to that red load yet. That red load, remember, was here. Okay, and we at the moment are here, remember, we're going along the beam. We haven't got to the 20 kilonewton load, so we're simply going to ignore that red term there. Okay, now the reason we know we're going to ignore that is because the Macaulay's term is negative. Okay, so we're just going to say that that is 0. We're just going to ignore that term. Now, mathematically, clearly, if you put x equals 0 into that equation, you're not going to get 0. You'll end up with minus 3 cubed which you would then divide by 6, times it by minus 20, you're not going to get 0. But we're just going to use Macaulay's method, and we're going to say, let's ignore that because we haven't got to that red term yet. Same with this green term. If x is 0, this is negative. So therefore, we're going to ignore that term. Like I say, mathematically, it's not 0. Of course, it's not. But according to Macaulay's method, because the Macaulay's term is 0, or negative, we're just going to ignore it. We haven't got to that green load yet. Same with this gold one. Negative, the Macaulay's term is negative. 0 minus 10 is minus 10. So it's negative. So therefore, we're just going to ignore it. We're going to say it's equal to 0. And then, so we've got x is 0. So therefore, that term there is clearly 0. So that disappears. That's disappeared. First one. X is 0, so that's 0. So we end up with now y is 0. This term is 0. So we've got 0 equals b. So b equals 0. Okay. So ignoring any negative terms, we can say simply by inspection that b must be equal to 0. Now, the other boundary condition that we had was this, when x was equal to 12, y is equal to 0. So this time, let's put x equals 12 in here. So it's not quite as simple this time. Here we've got 15 times by 12 cubed over 6 minus, now if we put 12 in there, 12 minus 3 is 9. That's positive. So therefore, we can't ignore that this time. And the reason we can't ignore that red term is because think of where we are on the beam. We've gone past that 20 kilonewton load and we're sat there. Okay, so we must consider the influence that that 20 kilonewton load has on the bending moment of the beam. So we've got 9 cubed over 6 plus, and again here, let's look at our Macaulay's term, x minus 6. If x is 12, we can end up with 12 minus 6, we end up with 6. That's positive. We must consider that. Again, because we have gone past that green load, we've gone past that 10 kilonewton load. So therefore, we must consider the influence that that has on the bending moment. Okay, there we've got our gold load, 12 minus 10, is 2. 2 cubed over 6 is positive. We've gone past it. We're here, we're 2 meters past it. So therefore, we must consider that load. So we've got 2 cubed over 6. Now, if x is 12, we've got 12a there. And we've already said that b is equal to 0, so therefore b has disappeared here. Now, if we therefore work out that, we've got one unknown, a, we've got one equation, so therefore we can work out what a is. So a is minus 184.2. So looking at this equation here, we can now write down, we know what a is now, we can write down an equation which tells me the slope anywhere on the beam. We also know what b is, so therefore we can write down an equation which tells me the deflection anywhere on the beam. So there we've got that. We wanted to find, there we go, it's there, look, there's our slope equation with a at the end, but now instead of a we've got a number, and there's my deflection equation, and we've got a on the end, ax, b is equal to 0, so that's why b is not there. But we've now got a general case, so this tells me the slope anywhere on the beam, and this tells me the deflection on anywhere on the beam. So if, for example, the question was asking us to calculate the we look here, if we wanted to find the slope at x equals, sorry, that's actually the deflection, not the slope. If we wanted to find the deflection at x equals 6, we would take the general case equation, this one here. So this equation here, you can see we've taken that equation and we've got that here. We've then said, well, at x equals 6. So x equals 6, we're going to put that into that term there, look. If x equals 6 here, so 6 minus 3 is 3, so therefore that term is there. So we must consider that. This term here, our Macaulay's term is 0, 6 minus 6. So therefore that term is going to disappear. So therefore that's 0, we ignore it. This term here is negative 6 minus 10 minus 4, so it's negative, so therefore we ignore that. Now the reason for that, let's consider where we are on the beam. We've gone 6 meters along the beam. We've gone past the 20 kilonewton load, we must consider that term, and we're now currently there where the green one is, hence it is 0. So we can ignore it. We haven't got to this one yet, so therefore that's why that's negative, and we ignore the term associated with that 30 kilonewton load. So when we're at x equals 6, we only need to consider this term here, the 20 kilonewton load, the moment caused by the 20 kilonewton load, and that is this one here, look, 20 kilonewton load. So 20 kilonewtons times by 3 cubed over 6. If we calculate that, we end up with that. And then in this question, in this scenario here, I've said, okay, let's put some typical values in for E and I. So let's say our E, let's say it's made from steel, 208 gigapascals. We've got a fairly standard I value. So the deflection in the middle of the beam, therefore, would be 38.4 millimeters. Okay, so that's how we'd go about using Macaulay's method with simple point loads. Okay, we've gone through, we've written down the bending moment equation, we've considered what all the Macaulay's terms are, we've then integrated them with respect to themselves with them when they're Macaulay's terms. We have worked out the constants of integration by considering the boundary conditions in exactly the same way that we did with the direct integration method. And then we've got the general cases, and then we've considered what the values for x is, whatever we're interested in, put those values in, and we just need to consider if any of the Macaulay's terms are 0 or negative, we just ignore them. Okay, so that's an example with simple point loads. So we've considered an example using Macaulay's method of a beam, simply supported beam with multiple point loads on it. What I want to think about now is how do we deal with a beam with multiple loads on, and some of those loads are uniformly distributed loads, UDLs. How do we deal with that? Well, the first thing that we can consider is what happens if we've got a UDL running over the entire length of the beam. Well, actually, it doesn't matter at all. That would just be a normal load. So if we consider this scenario here, we've got some sort of uniformly distributed load over the entire beam. We've got a reaction at A, a reaction at D. We've got a load here and a load here. Okay, so EI equals our moment. EI d squared y by dx squared is equal to our moment. So we've gone along the beam, started at the left-hand end of the beam. We've gone along past all of our loads to the point where it's most complicated. So we're at position X there. We're looking left and we're going to write down the bending moment caused by the loading on the beam. So the first term here, RAX, is associated with this load here. So we've got the reaction at A, and that is we've gone X meters along the beam, so therefore that is X meters away. Okay, so RAX, that's that term there. We've then got this term here. This is the term associated with our UDL. So our uniformly distributed load is sat on top of the beam all the way along the length of the beam here. Okay, so to the left of position X, we've got, so this load is W newtons per meter. So it's acting over X meters. Okay, so to the left of position X, the total force is W times by X. And where do we assume it acts? We assume it acts in the center. So if this distance here is X, it's acting X over 2 meters away. It's in the center. Okay, so if you take Wx, so that's the magnitude of my load, and multiply it by the distance to the assumed center of that load, X over 2, you're going to end up with Wx squared over 2. And that's that term there, look, Wx squared over 2. And then the other terms are exactly the same. As we were considering in the last example, we've got W1, and that is x minus a meters away. So that's that term there, minus W1 x minus a. And then you've got this term here, W2, and that is x minus b meters away. W2 minus x, W2 minus W2 x minus b. Okay, so the UDL does not require any special treatment associated with the macaulys term. It's not a macaulys term. It's not x minus a in brackets or x minus b or anything like that. It's just x squared over c. So that becomes you deal with that in exactly the same way that we would ordinarily. If, however, the UDL starts at b, we've then got this scenario that we were talking about earlier, where we've got one bending moment before the UDL, and we've got a different bending moment after the UDL. So the term associated with the UDL has to be a Macaulay's term. So there we've got RAX again, RAX. So that's this blue term here, RAX. And then here you would have, well, that's that term there. Our next term, the one associated with the UDL, because the UDL now starts at position B and runs along my beam, it is, so from the left of position X, the magnitude of the beam is W newtons per meter, but it's acting over X minus A, so it's WX minus A, W times by X minus A. And where do we assume it acts? Well, if this distance is X minus A, we assume it acts in the middle, so that's X minus A over 2. So it's WX minus A squared over 2. So that's where we end up with that term there. And notice now that is a Macaulay's term. You've got an x minus a squared term in there, or an x minus a term in there. That is a Macaulay's term. So you would deal with that in exactly the same way that you deal with Macaulay's term with your point loads. Okay, so the UDL becomes a Macaulay's term. There it is. We integrate it once to get the slope. We integrate it again to get the deflection. If that Macaulay's term is 0 or negative, when we're dealing with our boundary conditions to understand our constants, we just ignore them. And if we are looking at the final solution and we want to work out the loading at some point on the beam, if that term there is 0 or negative, it means simply we haven't got to it yet. So we must be in this region here. So we just ignore it. We just ignore that term. Okay, so if you've got a UDL which starts or goes all the way along the length of our beam, then it doesn't require any special treatment. If you've got a UDL which starts partway along the end of the partway along the beam and goes all the way to the end, it's just a Macaulay's term. However, there is a scenario where we can have a UDL which doesn't start at the beginning and also doesn't finish right at the end, doesn't go all the way to the end. Let's now consider how we would deal with that. Okay, so here's our scenario. We've got a beam. We've got some loading on the beam. We've got point load there. We've also got a UDL which doesn't run all the way to the end of the beam. It starts at this position here and it goes to that position there, and it stops. So how would we deal with that? Well, what we can do is that causes an issue in terms of that doesn't run all the way to the end of the beam, so we can't deal with it like we did in the previous example. So in order to be able to do that, what we can do is we can take that UDL and we can extend it to the end of the beam. And we would deal with that in exactly the same way that we dealt with it in the previous example. However, obviously now we've changed the loading on the beam. We've added this gold part here, we've added this part here. So clearly the slope and the deflection on that beam would change. So in order to counteract that, what we're going to do now is put an opposite UDL on the bottom. And those two forces would cancel each other out. But what we have now is a UDL on top of the beam, which starts here and goes all the way to the end of the beam. And we've got a UDL underneath the beam, which starts here and goes all the way to the end of the beam. So we could deal with those in exactly the same way that we did in the previous example. The only difference is that one UDL now is on top of the beam, so therefore it's positive, and one UDL is underneath the beam, so therefore it's negative. So we can deal with that So there's our UDL. We've got our UDL. So to start with, it's in red, this bit here. We've then extended that to the end of the beam in gold. There's our UDL running to the end of the beam, W newtons per meter. We've extended it, and we've put an equal and opposite force in green underneath the beam. There's our UDL underneath the beam. Okay, so we'll deal with that in exactly the same way. Okay, so we'll start on the left-hand end, we'll go down the beam, we'll go past W1, we'll then go past the red UDL, and then we'll go to this part here where we're now in the gold and the green UDL. So we're going to write down the bending moment equation. So it's as complicated as it gets. Okay, so we've got RAX, our bending moment, equals EI d squared y by dx squared. That's equal to RAX. That's the moment associated with this force. Okay, so we've gone x meters along the beam, so therefore it's x meters away, so it's RAX. And then we've got minus W1. Let's put that in pink. So this moment here is associated with that force, minus because it's downwards, W1, and it's x, x, this distance here, minus a meters away. It's a Macaulys term. We would deal with that in a Macaulys term in exactly the same way that we did with the example with the point loads. We've then got this term here, which is associated with the UDL sat on top of the beam. Now that is W newtons per meter over this distance here, so this red bit, and also this gold bit that we've added on here. Okay, so that's W newtons per meter, and that's acting over x minus a meters away. X minus a, W newtons, x minus a. So this term here is associated with that. So this term here is associated with the red UDL, which actually we've extended. And so it's also the gold UDL. It's the red and gold UDL sat on top of the beam. Okay, so negative because it's acting downwards. And then we've got this green UDL, which is acting on the bottom. Okay, so therefore it's positive, and that is W newtons per meter acting over x minus b. X minus b. Where do we assume we act? We assume it acts in the center. That's x minus b over 2. So you end up with w x minus b squared over 2. So that term there is associated with our green UDL sat underneath our beam. Positive because it's acting upwards. So you can see by doing that, we can deal with UDLs which don't run all the way to the end of the beam. We just extend them and we just put an equal and opposite load underneath the beam to cancel out any change in loading that we've put on top of the beam. Okay, so what I want you to do is have a look at those, check you're happy with those examples, with those, you know, how you would do those, and then try those examples. There are 1, 2, 3 examples at the end of that handout using Macaulay's method. Have a go at those. I will upload this handout which talks about Macaulay's method, the theory of it, and it's the same handout that we looked at last time, which is looking at the direct integration method, and it explains the theory of slope and deflection of beams generally, this idea that EI d squared y by dx squared is equal to our moment. And I will also upload this worked solution, this handwritten handout, which talks a little bit about the theory and then explains some of the derivations that we've gone through, and also has worked solutions to those questions that I've asked you to do. Okay, so have a look at those. Any questions on any of that, let me know, drop me an email or speak to me in class, and I will speak to you soon. All right, cheers, bye-bye.